So how do we sense blood pressure? So what's going on in the body that allows the brain to know what's going on with the blood pressure? To answer that, we have to think about the reflex arcs that we talked about a bunch of weeks ago. So remember, a reflex arc involves some sensory information, some sensory structure, delivering information through the afferent pathway back to the central nervous system, to an integration center, which may be the spinal cord, maybe something in the brain. And then that integration center is going to send an efferent signal back through the efferent nerves back to some effector organ. So that's just a general reflex arc that we talked about previously. So how does that reflex arc play out in terms of sensing blood pressure? Well, the sensory structures in sensing blood pressure are located in two places in your heart. First, they're located in the arch of the aorta. So there are a couple sensory structures in there, some stretch receptors that are sensitive to pressure. So if the pressure in the aorta increases, what's going to happen? The wall of the artery is going to, the wall of the aorta is going to stretch, and those stretch receptors, those mechanically gated channels, are going to stretch open. They're going to allow sodium to flow in. It's going to oh my gosh, we're going way back to early stuff in this class. So the sodium, those stretch gated channels are going to allow sodium conductance to increase, which is going to depolarize these cells. That's going to bring the cell to threshold. It's going to fire an action potential. That action potential is then going to propagate from the sensory structure back through the afferent pathway to the central nervous system, to the integration center. We have a very similar population of these in the carotid body here, which is the place where your carotid, your common carotid artery bifurcates into an external carotid and an internal carotid, which is where you feel your pulse in your neck. So there's another population of these same stretch receptors that are located at that bifurcation of the carotid artery, and both of these populations are very well placed, right? Because if you wanted to sense blood pressure, would you want your sensors to be at in your toes? Probably not. You want it closer to the source, because the heart is the thing that's producing the pressure. So the aortic arch is a very good place for Mother Nature to have placed these receptors, and also the carotid artery is delivering blood to that really important structure. What is that? The brain. Yeah. So between these two populations, these are both working the same way. If the artery stretches, it's going to stretch these mechanically gated channels. Sodium's going to inflow. That's going to send bursts of action potentials toward the integration center, which in this case is in the medulla, so part of the brainstem. The medulla contains the cardiovascular control center, which is where these sensory structures are going to move. So those neurons are going to be constantly monitoring the mean arterial blood pressure. And so a normal mean arterial blood pressure, remember if your blood pressure is 120/80, which is a good resting blood pressure for a healthy individual, that means the mean arterial pressure, if you did the math, you would find that it's 93 millimeters of mercury is a resting mean arterial pressure, because it's diastolic plus 1/3. The difference between systolic and diastolic would be 93 millimeters of mercury. It's actually 93.333, but so 93 millimeters of mercury. What happens if the mean arterial pressure increases, like during exercise? Well, now those sensory structures in the carotid, in the aortic arch and in the carotid sinus here are going to perceive stretch, and they're going to fire action potentials, and the rate of action potential production is going to increase here, shown in this middle figure here. That's going to send action potentials to the cardiovascular center in the medulla, way up here, and the cardiovascular center. Remember, the medulla is the site of origin of the autonomic nervous system, and it's greatly influenced by the hypothalamus. So the medulla is going to be able to take that stretch information from the cardiovascular system, and it's going to be able to tell the sympathetic nervous system, slow down, don't do so much to the heart and to the vessels. And it's going to tell the parasympathetic nervous system, increase, because we've got too high pressure. So we've got to let off the accelerator and apply the brakes a little bit on the cardiovascular system. And that's going to have the effect of then sending this efferent information, this decreased sympathetic and increased parasympathetic tone to the heart. What happens if we decrease sympathetic tone to the heart? What's going to happen to the rate and what's going to happen to the force of contraction? They're both going to go down, and that's going to decrease pressure. What happens if we increase sympathetic tone to the heart? How's that going to affect rate? Going to drop it. What's going to happen to force of contraction? No big change. So the sympathetic is going to affect the rate. The decreased sympathetic is going to decrease the rate and the force of contraction, both of which are going to have the effect of decreasing the pressure, relieving the stretch on these sensors, and then the medulla is going to say, okay, now the sensory information isn't telling me that there's high blood pressure, so I'm gonna release my control on the autonomic nervous system. Of course, the autonomic nervous system has more influences than just these cardiovascular stretch receptors in the aortic arch and in the carotid bodies. They've got influences coming from the hypothalamus. If you're terrified and you need to run away from a bear, you're probably not, your medulla probably isn't going to pay a lot of attention to the stretch receptors because the blood pressure is high. Rather, it's going to pay attention to your hypothalamus that's saying, holy cow, I got to get out of here. So the blood pressure consequently is going to rise, even though these receptors are firing and saying high pressure, high pressure, high pressure. The pressure is going to remain high because your body has other needs that are seemingly more important than maintaining the pressure. But if nothing else is coming in, if the hypothalamus is under control and there's no emotional or other influences where you're saying, I've got to be running a marathon or I've got to get to the reg before my final starts or whatever, then these receptors are going to fire and they're going to take control of the pressure. So this is the cardiovascular, this is the baroreceptor reflex arc. From the sensors to the afferent, to the integration center, to the efferent, to the effect, okay? Good. So this is another, oh, I'm sorry, many hands,
sorry.
yeah.
I just got a little
Go back.
confused. You said if you decrease the sympathetic tone, you decrease the rate, and it doesn't have an effect on the voice?
No, I'm sorry, yeah, maybe I blurred that together, right? If you decrease the sympathetic, you're going to decrease the stimulation of the autorhythmic cells, which is going to have the effect of decreasing the rate. You're also going to decrease the effect on the contractile cells of the heart, which is going to decrease the force of contraction. And since cardiac output equals heart rate times stroke volume, both of those are going to go down, and that's going to have the effect of decreasing mean arterial pressure. What I said, I think what I maybe spoke too fast about is that the parasympathetic is only going to affect the rate. It's going to, if you increase the parasympathetic stimulation, it's going to have the effect of suppressing the rate of the heart. It's not going to have any direct effect on the force of contraction because there are no parasympathetic nerves that go to the contractile cells by and large. Okay? Yeah.
So this is so the only. Are you saying the only real ways that the body senses pressure is through these two receptors here?
There are other ways, but these are the biggies.
So this is also how it feeds into regulating arterial dilation as well, throughout the body. It bases it on these measurements.
So are you talking arteriolar dilation?
Yeah.
Yeah. So it certainly uses these, yeah, because the output of this, if you decrease the sympathetic stimulation, what is that going to do to the alpha-1 and beta-2 receptors throughout the circulation? It's going to decrease that. So you're going to have less vasoconstriction of those alpha-1 receptors on the arterioles, less vasodilation of the beta-2 receptors, and so it's going to have the effect of just sort of cutting decreasing the autonomic control over those arterioles, which is going to have the net effect of dilating and lowering pressure. Good. Is there anything else? Yeah.
Don't arterioles constrict and dilate in a location-specific way?
They do. Yeah. This doesn't. So the local effects are still going to have the effect of having that. The increased carbon dioxide, decreased oxygen. The myogenic effect is still going to have an effect. This is only influencing that autonomic influence, which is one of the three. It's actually the big of the three effects that's going to change arteriolar tone. Okay. Good. All right. Nice. That's a chin scratch. Okay. Good. So this is another one of these figures that pulls together a whole lot of stuff that we just talked about. So remember, mean arterial pressure is equal to cardiac output times total peripheral resistance. So remember, controlling mean arterial pressure is the name of the game of the cardiovascular system. In a perfect scenario, if we were perfectly trained animals, our mean arterial pressure, you're learning in lab, would not change from times of rest to times of activity. None of us is a perfectly trained animal, so our mean arterial pressure is always going to creep up with increased activity. So let's think about what goes into the mean arterial pressure. Cardiac output equals heart rate times stroke volume. Total peripheral resistance is influenced by the radius of the arterioles and the blood viscosity. We haven't talked about this one yet. We'll get to this in a couple of weeks, so don't bog yourself down with this. But you can imagine that if the blood became more viscous, the resistance to flowing that blood would change. If viscosity increases, if it gets syrupier, that would make the blood harder to push through the arterioles, and it would increase the total peripheral resistance. We'll disregard that. So let's just think about arterial radius. So if the radius increases, that's going to decrease resistance. If the arterioles constrict, that's going to increase resistance. And then all these other influences, I'm not going to go through them right now just for the sake of time, but this is a really good thing to study to kind of get your handle, get your mind around everything that's going on.